Question 9.1 is another question that's based on a past exam paper. This question is asking us to analyse, well, in the first part, this system. We've got a mass which is attached via a cord over this pulley to this light bar here, which is in turn connected to a ground via a few springs. And in the question, it leads us quite sort of kindly through the process which will generate a second order differential equation, and from there we can evaluate what the natural frequency of this system is. Now, the second half of the question then asks us to work out what happens when you put a damper in there, a dash pot, in place of one of the springs, but we'll get to that in a bit. So let's start with part 1 that asks us to calculate the kinetic energy of the system as a whole as a function of the velocity v of the body. So we want kinetic energy as a function of v, and we're given other properties of the system like the mass, the moment of inertia and the radius in the question. So let's use a symbol T to denote kinetic energy, and there are two components to kinetic energy. There's the kinetic energy of A, which is in pure translation, but there's also the kinetic energy of the pulley here, which is in rotation. So the kinetic energy of the mass A is simple enough. It's just half mv squared, and m is given in the question. That's 2 kilograms. So that's simply 2 divided by 2 is just v squared. Now the potential energy of the pulley in rotation, well, we need to use half I omega squared to evaluate that, where I is the moment of inertia and omega is the angular velocity of the pulley. And if I just remind you of how angular velocity relates to tangential velocity, if that's omega, then the velocity downwards, which is the velocity of our mass in this case, because this is all connected to the mass A here, the angular velocity is connected to the tangential velocity by v equals omega r, where r is the radius, so that distance there. That was in lecture 4 that we went through that. So the radius of this pulley is also given in the question. So we can substitute omega. If we rearrange that, we get omega equals v over r, and you can substitute that into there to get half I v squared over r squared. So if I now find out what I and r are from the question, well, I is equal to 5 times 10 to the minus 2 kilograms meter squared, and the radius is 80 millimeters. So now I can substitute these values into there and evaluate what this is. So let me just do a quick calculation. Half times I, 5 e to the minus 2, divided by 80 e to the minus 3 squared. 3.91. 3.91 v squared. We just draw a little box around that so we don't confuse it. So the total kinetic energy then is the sum of those two components. So v squared plus 3.91 v squared, so it's 4.91 v squared. And that's the answer to the first part of the question. So the second part of the question asks us to calculate the potential energy of the system as a whole, and this time in terms of x, the downward displacement of body A. And we're told that the springs are unextended at x equals 0, and that makes things quite convenient for us when evaluating the potential energy of springs. So there are two sources of potential energy. Potential energy because the height of the elevation of A is changing, and also potential energy stored in those springs. Those are the only two components. So potential energy of A, we just use mgh, and h in this case is the elevation, and that's equal to minus x, because x is going downwards. So we're told m is 2 in the question, so if I just put minus 2 times 9.81 for gravity, that's minus 19.6x. So the potential energy in the springs, we can use our expression for spring potential energy, which is half k s squared, but there are 3 of these springs, so it's going to be 3 times half k s squared, where s, if you remember, is the stretch. And the stretch in this case, well, if this has moved downwards a distance x, then this would have moved up a distance x, so the stretch is just x. So this goes to 1.5 k x squared. And k, which is in the question, is 80 newtons per metre. So 80 times 1.5 is 120 x squared. So the total potential energy is the sum of these two things together, so it's 120 x squared minus 19.6x. And that's the part 2 done. So part 3 says, now using the principle of work and energy, derive the second order differential equation. So we'll do that, and because there are no non-conservative forces, these are just conservative forces in this system here, we can use our expression for principle of work and energy as the potential energy plus the kinetic energy is a constant. So if I now add these two together, we'll get 4.91. Instead of using v, I'm going to use x dot, which is the time rate of change. I'm just going to use that symbol, it just makes it a little bit neater. So x dot squared plus 120 x squared minus 19.6x is equal to some constant. Now what we did in lecture 7, if you remember, is to, when we get to this point where we've constructed potential energy plus kinetic energy is constant, we differentiate with respect to time. So we differentiate with respect to t, and don't forget the chain rule, which is dx dot, that equals x double dot x dot times 2. And you can go over previous tutorials where I explain that a bit more carefully, but that's just to remind you of how you differentiate something using the chain rule. So this would then go to 2 times 4.91 x dot x double dot plus 240 x dot x minus 19.6 x dot equals 0. And we can divide by x dot, so get rid of that, that makes things a bit neater. And I can divide by 2 actually. Anyway, so I'm going to rearrange that. That gives x 4.91 plus 120 x equals 19.6 divided by 2. It doesn't really matter what's on the right hand side. This just tells you that it's not in equilibrium at x equals 0. You could work out where it was in equilibrium by setting that to 0 and finding out what x was. That would be your equilibrium position. But don't worry about that. What we've managed to do is put this in a form which is a generic second order undamped governing equation. And if you remember from lecture 7, and it is in your data books if you want to look it up, in fact I'll show you. Oops. If you look here, this is a second order undamped system, mx double dot plus kx equals 0. And when you're in this form, you know that the natural frequency is the square root of k over m, where k is the constant in front of the x and the m is the constant in front of the x double dot. So in this case we have the natural frequency being equal to the square root of 120 over 4.91. So that equals 4.94 radians per second. So that's question 3 done. So now, this is the last part which actually relates to damping, is it says we've replaced one of the springs with a linear damper. We're told that damping constant is 50 newton seconds per meter, and we're asked to rederive the second order differential equation that describes the motion of A. So to do that, a lot of this will be the same, and we'll be using this again, except there are 2 springs this time rather than 3. So the only difference will be here. This won't be 3, that will be 2, which means this will just be like that. That will be 80, and this will be 80, and this would have been 80. That would have been 120. No, not 120. Something else. Anyway, let me put that back as it was. It will be 240 times 203, 160. Okay, and then that means that this will be just 80. So, but what I haven't done here is taking into account the damper, of course. This is just changing it from 3 springs to 2 springs. So, when dealing with a non-conservative force, we can't use the potential energy plus the kinetic energy as constant anymore. We have to, and this is from lecture 3, use that expression. So the potential energy plus the kinetic energy minus the work done by non-conservative forces is constant. So we know what the potential energy due to the springs and the changing elevation of the mass are. We know what the kinetic energy of the translating mass and the rotating pulley are. But the work done by the non-conservative force, so the damping force, we can use the fact that the work done is that damping force times, integrated over position, so the displacement x in this case. And if you remember, the damping force is equal to minus the damping constant times x dot, we're given the damping constant, by the way, it's 50. We can substitute that into there. But also, if you remember from lecture 9, instead of having the work done described as an integral over distance, we can describe it as an integral over time, provided we multiply x dot. So we multiply the force by x dot. Those two things are now equivalent. And when we eventually come to differentiate that, this will drop away nicely. So we're going to shove that into there now. And it will equal the integral of, so I'll take the minus outside, c x dot squared dt equal to minus 50 x dot squared dt. So everything else was the same, and if we look at what that was like, so v plus t just gave us this 4.91 x dot squared. So let me write that again, 4.91 x dot squared. We had an 80 x squared from the spring, the two springs, and we had this minus 19.6 x, which was from the potential energy of the changing elevation of mass A. But now we've also got this u term, and it's minus u, so it's plus 50 x dot squared dt, and that's equal to a constant. Now we do exactly the same things as before. Differentiate with respect to time. We get the 2 at the front. We get 160 x dot x squared. Sorry, no, x dot x. I think that's right, yeah. And we get minus 19.6 x dot. And when you come to differentiate that with respect to time, it just goes to x dot squared. Now we divide through by x dot. And what we're left with when we collect terms together is, again, similar to what we had before. I'm going to divide through by 2 again. So we'll get 4.91 x double dot plus 80 x. Then, sorry, this was, should have had a 50 in front of there. Plus 25 x dot, and then 9.8 on the other side. And that's the governing equation. I think in the worked solution it's just multiplied the left hand side and the right hand side by a factor of 2, but it gives you exactly the same thing. Okay, so that's everything there is to that question.